morning. Seems to me maybe a lot of people are sleeping, or still sleeping, all touring this beautiful city. I went to, I called taxi this morning and I went to Hierarchical and banana port. So I toured the city in the morning myself. Yeah, it was good, beautiful city. And if you have done so, you should do it. I would recommend you should tour the city and see the beautiful scene. It's first time being here, and I've been here just one day. Arrived yesterday and leaving today. So I thank you for letting me talk first. I have an airplane to catch. All right. So the title of my talk is Hierarchical Distributed Fault Computing Architecture for Big Data Analysis in Smart Cities. Actually, my student was supposed to come to give a presentation, but he couldn't make it, so I come, a last minute decision. All right, here's the outline. I will give a brief introduction to start with, and then we look at the challenges, the issues that we have to solve to build a smart city, and the current progress. Then we introduce the new architecture that we proposed, sponsored by National Science Foundation of the United States. Then we'll go through this hierarchical distributed fault computing platform. We did a proof of concept implementation prototype. We made a prototype, and the prototype is working. If anyone is interested, you're welcome to come to visit to look at the prototype. So this is the outline. So there is a growing urbanization in the world. The population in the city is getting bigger and bigger. But the resources are limited. In order to manage the resources efficiently and effectively, this smart city concept was proposed very recently. It is growing very fast. Now, the essential thing of this smart city is a large amount of sensors deployed all over the places, like infrastructure, smart grid, transportation, healthcare, education, entertainment, whatever you name it in the city. So you deploy a huge amount of sensor, then you collect a huge amount of data. So you're going to deal with a huge amount of data. So this is why we submit paper to Big Data Conference. Actually, my research used to be in computer architecture and data storage, computer network. And this is the first time we come to conference. And that's why I see all the new faces here. So with this big data, urban analytics, and smart community, self-driving cars, smart grid, okay, name a few, right? So challenges facing the smart city. We have large-scale sensor network, big data analysis, machine-to-machine communication. Right? Now the market is predicted to be huge. Right? We're talking about like 25. Actually right now in San Jose, California, the city government and a few companies like Intel collaborate to start this smart city project. And this project created 25,000 new high-tech jobs in San Jose. And the market is going to be like $1 trillion. And we're talking about $3.3 trillion by 2025. So it's growing fast. Now, current progress, basically right now, we in the smart city, we just deploy sensors, then we use cloud computing to do intelligent computation, data analytics, and decision making, and doing first responder for event. Now, when you generate a huge amount of data from edge devices like sensors, you send the data to the cloud. Cloud upload data to cloud for computing, and return data back to the local devices for decision, right? Like optimize, energy distribution, optimize traffic, healthcare, right, things like that. These decisions are made at edge devices, but it is computed at the cloud. Now, challenges with cloud computing, because the data is increasing fast, exponentially. You're going to transmit a huge amount of data from end device, from servers, from sensors to the cloud. And this data transmission consumes power, consumes resources, and consumes the net value. And there's also computation burden because everything is done in this cloud. To solve this challenge, we propose a new computing architecture called reflex tree. Right? And this reflex tree architecture was, sponsored by the National Science Foundation. And we got a big grant to work on this project. But this paper will talk about fog computing because this is an industry term proposed by Cisco, fog computing. Right? Cloud is in the sky. Fog is same thing but lower. Right? And the ground, same as cloud, but closer to the ground, and is basically in this context is edge device, right? So we sense data at local devices, right? We receive data from local sensors, perform. So we use low cost, like smart dust, right? Low cost, smaller, embedded computer systems deployed together with sensors to do latency sensitive computation at a computing node, right? Sometimes you don't need a huge computing power, but you need a quick response to make decisions depending on what event happened. And we upload high-level data to the intermediate computing node, the second layer. We got first layer, second layer, third layer, fourth layer is cloud. The top layer is cloud. So we got 4-layer hierarchy. Now, advantage is, geo distribution, and it supports Internet of Things, which is very hot today. Smaller, smart devices, and quick response and control. I got music from you. That's good. Thank you. I was wondering where the music comes from. Yeah. So this is the architecture we have built. So the top layer is cloud, and this community computing, neighborhood computing component, and the infrastructure at the bottom. And we come up with a new type of sensor for monitoring a variety of devices and facilities. And this is this sensor is based on optic fiber that we use for communication. It's a thin fiber like thin as a hair. And we currently use that for internet, for data communication. But we can make use of that fiber optics without negatively impacting the communication performance, and we use that for sensing. Right? So actually, it's using optic fiber, but using a different band for sensing, and the sensing resolution is as high as like a few millimeters or millimeters. So you can sense information at millimeter resolution, but it's So it's kind of, make a better use of the infrastructure that we already have, right? Because in the United States or here, Taiwan, I think China, they all have this optic fiber communication infrastructure. So we can make use of existing infrastructure to do sensing. The advantage of the sensing network is there's no need to charge battery. But if you deploy wireless sensors, you have to use battery, and the battery runs out, and you have to recharge it. It's difficult if you have, imagine you have millions of sensors, wireless sensors, and you want to recharge battery. That's huge, prohibitive cost task, right? But with our sensor, there's no need to charge battery. You don't need battery, it's passive sensor. So that's lower layer. And this the second layer, we build embedded computers that can do simple analytics tasks. Actually, we have already implemented a hardware SVM using FPGA that can analyze data, filter data, and using a small embedded FPGA. But that FPGA can be built as an ASIC. I connect directly to the sensors network. And that's the layer, this layer. And on top of this, we can have intermediate computer. This will be like PCs and servers. Eventually, the data after analysis will be forwarded, transmitted, or uploaded to the cloud. So this is our prototype with this lab scale pipeline monitor system. So this is real pipe, and we use this pipe to transmit gas, propane gas, for cooking, right? For cooking, for heating, it's gas. It's an energy supply line. So we use this. We build this pipe, and then we build sensors. We basically just deploy this fiber optics along this pipe. And the sensing fiber optics can, detect all kind of, can sense all kind of information like temperature, pressure, stress, all kind of information. And that information can be transmitted using different band through our ASIC or FPGA device. So we have implemented this sensor, this real-time distributed fiber optic sensor. Now we also implement extra pattern as features. This is we use the embedded processor that feature extraction. So this is the image of this. If it's normal, everything normal is just like if something happens, it can happen. So we use our machine learning algorithm, feature extraction, apply sequential learning model, like hidden Markov chain, Markov model for visitors event detection. And layer 1 is block computing, collect data and event information from layer 2 from very large scale, citywide. So we just have a local, we skip layer 3 because we just have a smaller lab. We don't have like neighborhood, we don't have district, so we just did in a lab. So this data with first do the feature extraction, do simple HMI, then send the result to the cloud. So with lab scale pipeline system, we generate heating and cooling process. So we have total of 100 groups of data. 6 seconds between each group. First 40 groups heating process, 41 to 100 stop heating and cooling process. So we repeat this process. The data set about 205 sensing point, and each we didn't do the millimeter, we just said centimeter apart. Imagine lithium temperature change based on room temperature. So with this regular fault computing architecture, we monitor temperature with distributed fiber sensors, extract features, use machine learning algorithm like HMM, and upload results to cloud. And we use this HMM to do this data classification, event classification, build this ICM ourselves for each predefined event. Actually, the ICM was the other paper published in ICPP in Beijing this past September. So for this paper, we use this ICM. We classify new sequential data with maximal, posterior probability. So here is the result with different number of hidden state. So this is the Q from 2 to 4, and here is a different number of Gaussian component, and here is the data reduction in terms of what you need for the network from end device to the cloud. So this blue line is for fog computing. That's what we did, and this at both layer 2 and 3, and the green line is for computing at layer 2 only, and the red line is just the traditional cloud computing without fog. Right? As you can see, the amount of data you have transmit over the network is reduced dramatically with this fog computing. Obviously, if you did data filtering and data analytics and the end device, you don't need to transmit the raw data to the cloud. So conclusion and summary. So a fog computing structure for smart city was proposed. Dealing with big data, sensing structure, computing structure, and we build a prototype. This hierarchical distributed fog computing platform introduced within 4-year smart city system, and we did a proof of concept prototype. A lab scale gas pipeline was built and monitored and analyzed. A case study and experiment result demonstrate its effectiveness, and this research of NSF project Smart City. That's all. Thank you. Questions? Yeah. So the fog computing, basically, the cloud computing, you sense the data and using sensor. The raw data will be transmitted to the cloud. Cloud will do the data analytics. Right? So this figure shows the amount of data you have to transfer over network. With fog computing, right, some of data in analytics is already done in edge device. So you transmit only the important data up to the cloud. So the purpose here is reduce the network requirement, reduce power consumption, and increase, actually minimize response time. So you can respond quickly at each device. For example, if you have local gas line in your neighborhood, right? If there's a leak, you can immediately respond by reroute the gas from an alternative line instead of keep leaking. Leaking is dangerous. If you leak, you get fired. So if you find a leak, you just locally control the pipeline, switch off that part, and reroute the gas supply through other pipelines. So you can do decision quick. Otherwise, without that, you would have to send the data to the network, the cellular network, to the cloud. Then cloud to the analysis, compute, oh, there's a leak, you come back. So it might be too late. So if you have a local computer device, do some simple analysis, and you can determine what happened and respond quickly. Yeah. Data size. Response time. Yeah, this is response time. Response time. Sorry. This is amount of data. This amount of data is response time. Yeah. Thank you. Well, I still prepared a slide. I didn't look at it. You have a question? No? Thank you. Thank you. You're welcome.